Good morning, everybody. Glad you're here. Feels like there's a little bit of positive energy this morning in this room. Is there some sort of exam going on? Like, are people trying to psych themselves out? Oh, finished exams yesterday. Okay, right, yeah. You can always tell when the engineering and science students are having bad exam weeks because nobody's talking and everybody's wandering down the halls like they want to change their major. Chapter 10, homework, is not due this weekend, right? It's kind of due the weekend after. That's because I was a little bit worried that in my past planning for the future, which is now, I got that temporally correct. I was worried I wasn't going to finish chapter 10 today. I still might not finish chapter 10 today, and it might roll over into Tuesday. And I don't like giving you homework until I am finished the lecture. I don't think that's fair. So that's why chapter 10 is due not this Saturday, but next Saturday. And beware, chapter 10 is like the huge chapter for this unit. So really get a jump on it, right? Yes, it's not due Saturday, but really work on it today, tomorrow, right? Do your due diligence on it, get ahead, because chapter 11 is also pretty meaty, right? But chapter 10 sort of has most of the different pieces of content in it. Hopefully you saw the announcement. GRASP is opening tomorrow at 8 a.m. I will not be there, but you'll be well taken care of by Dr. Kerfoot. He'll get the door open, the tutors will be there, and then the rest of the faculty will show up at their assigned times. I'm getting more shots in my back, my lumbar this time instead of my neck, so I'm really looking forward to that because standing on my right foot right now doesn't feel good. So hopefully we'll get that fixed for a little bit. The drugs only last so long. All right, we were talking angular work and energy. And I sort of laid out this idea that in addition to kinetic energy for things translating or moving in a straight line, we also have kinetic energy associated with the rotation of the object. In the case of something that is rolling, we have both of those things. The center of mass of the tire is moving in a straight line. That would be 1/2 mv squared. And it is rolling or turning, and that would be the 1/2 I omega squared. We took a very big tangent, not so much tangent, but a necessary evil into the idea of moment of inertia. I introduced you to the table and how to put things together with that table. But what I want to do now is I want to do an example of working with this conservation of energy, but for things that are now rolling, right? And we'll do the example of a bowling ball. We're going to compare and contrast here. What we're going to do is we are going to do one like we did back in chapter 7 and 8. Okay? We're just going to assume it's not rolling, it's just an object going down a hill. And then we're going to compare the answer we get for that. It didn't do its thing. There we go. We're going to compare the answer we get with that with the answer for what happens when we include the rolling motion. So let's get this set up here. We're going to paste another one over here. Okay, so I'm going to have the two setups, right? And in the first one, the ball, right, is just going to slide down a frictionless ramp, right? There's no friction here. So when we set up our conservation of energy equation, there's not going to be any work other. Now, we already know the answer for how fast it's going to be going. Does anybody want to guess how fast it's going to be going? We've done this before. No? No? Whenever you are asked for how fast something is going and when it goes down something, and you're lost, your guess should be the square root of 2gh. Yeah, like it just kind of comes up every single time. I'll do it again, right? But you'll see where it comes from. So no work other, right? No work due to kinetic friction or anything like that because it's a frictionless ramp. It starts with potential energy based on how high, right, above the 0 point it happens to be. I'll put my initial, put my final down there. Get too excited. Final, initial up here. And then my energy final is going to be 1/2 mv squared. The m's cancel. I multiply both sides by 2. I reverse the direction, take the square root, and I've got the square root of 2gh. Again, it's such a common result. And it's the result for when there is no friction. And it doesn't matter if the object is going down a hill, being dropped, right? Gravity doesn't care about any of those things. The speed that it will be going will be square root of 2gh. However, that changes when things roll. With rolling, with any kind of kinetic friction, it's not the square root of 2gh, and you got to get into the details. But let's go ahead and do the case where this object will now be rolling down the hill, right? It's going to have some sort of rotational velocity associated with it. Of course, it starts up there with no rotational speed and comes down here and has a lot of rotational speed. I still put my 0 here, okay? And I go ahead and I write out my conservation of energy statement. Now, work other, right? Work other is when there is any force besides gravity and springs. And now we're going to add one more to that list, which is the static friction that is there to cause something to roll. If this hill were frictionless, if the second hill were frictionless, would the bowling ball roll? Not at all, right? We need static friction in order for an object to roll. But static friction doesn't end up, that static friction that causes things to roll does not end up in work other. We're taking care of it with 1/2 I omega squared, right? That's where that static friction is. So just be aware of that. Work other is still kinetic friction, and anything that isn't a spring, isn't gravity, and isn't rolling. So again, even though there is enough friction to get this to roll, it's not slipping or sliding or doing anything else. So my work other is going to be 0. Up there at the top, is it moving? No. Is it rotating? Is it at 0? No. So that means, yes, I have to include mgh as my initial, right? When we get to the bottom, though, this is where things change. Is the bowling ball moving? And when I say moving, what am I meaning? Not rolling. Is its center of mass going somewhere? Right? Is the object in motion? Does it have V? Yes or no? Yes, right? Okay. It moved down the slope. It's got V. So what do I write down if it has V? 1/2 mv squared, right? And again, that's like a center of mass speed, right? Of the bowling ball. What's the new question we're going to ask because of chapter 10? Is it rotating, right? And is it rotating if it's rolling? Yes, it is. So what are we going to write for that? It's 1/2 I. It's not m. It's the rotational mass. It's the moment of inertia, I, and then it's the rotational speed squared. So that's the new, right? This is the new term, okay, that gets introduced because of chapter 10, and now that we're rolling and we've got radii and moments of inertia and all that sort of stuff. Okay, so we go for it, right? We want to know how fast it's going when it gets to the bottom of the hill. So what am I going to solve for? Oh, omega or V? The answer is yes. Both. But you're like, wait a second. Aren't there two unknowns here in just one equation? True. So that means we got to find a relationship or get another equation somewhere or something, right? We can't just make up equations. But is there a way, are V and omega related? Do they talk to each other? Do they need Google Translate? What's the relationship between V and omega? Woo, yeah, good. The velocity is equal to r omega, the velocity of the center of mass. That says V com. I didn't, my writing's too small now. C-O-M, the velocity of the center of mass, right, is equal to the radius of the bowling ball times omega, the rotational speed of the bowling ball. So what this means is I could solve, for omega. It's going to be V over R. All right? And now that I have a relationship between omega and V, I can go ahead and stick it into there. So I've managed to figure out my omega. Right? What about moment of inertia? We don't know what that is. They don't tell us anything. They just tell us the bowling balls are identical. Great. Okay. But I need to suss out the moment of inertia a little bit more. So how am I going to do that? The what? The table. Right? We're not going to integrate. We're going to go to the table. Okay? So we look at the table. We try to find a bowling ball. Where's the bowling ball? It's H right here, right? Okay, the thin-walled hollow sphere. Somebody did the math for me already. It's 2/5 total mass of the ball, radius of the ball squared. So back over here. So my moment of inertia, right, is equal to 2/5 mr squared from table. Why would I write down from table? Well, yeah, it'll be on, but like, why would I do that? I mean, obviously, I just got it from the table. Why would I write it down? When future you is trying to figure out just what the heck happened here, what are you going to want? Notes from past you telling you what you did, right? So leave notes to yourself. It helps a lot. All right. So what have I got? I've got mg8. So well, that stayed the same. All right. 1/2 mv squared. I just kind of want to leave it there because it's nice. But I can't do that. Okay. Plus 1/2. And then I put in my 2/5 mr squared. And then I put in my omega, which is v squared over r squared. I'm really starting to panic now. I mean, there's a lot going on in here, isn't there? But is there a ray of sunshine? Is there a rainbow on the horizon? Are there good things that are about to happen? What's going to cancel? Oh, the mass. I have the same mass in every term, right? Which means I can divide every term by the mass, effectively canceling it out. I like that. So I don't need to know the mass of the ball, which is interesting. Did I need to know the mass over here? Not at all, right? Just gravity didn't really care, okay? So it's kind of nice to see the same sort of physics idea falling out, right? It doesn't matter if this is a rolling elephant or a rolling bowling ball. The image of a rolling elephant was very disturbing just now. I'm sorry that I said that. Yeah, anyway. What else happens here? Oh, the r squared. Oh, good. I wasn't given the radius of this ball. So it doesn't matter. Big bowling ball, small bowling ball, golf ball. Okay, all right, fine. Small elephant? No. All right. Anything else? Ah, the twos. I got a 2 on top and I got a 2 on bottom. Algebra is useful sometimes. All right. So GH equals 1/2 V squared plus 1/5 V squared, right? That whole mess, it looked bad for a moment, didn't it? Like there was a lot of stuff that was kind of coming together. It was like, brrr, it was growing. It was turning into this big algebra monster. And then all of a sudden, right? Love it. Okay. Oh no. Now I have to add 1/2 and 1/5. If Peter has 1/2 of an apple, Jane has 1/5 of an apple, how many apples do they have? Is it 7/10? It's 7/10, isn't it? I was not good at fractions when I was a kid. All right. I was like, why would anybody have 1/5 of an apple? This is 7/10 v squared, isn't it? Which means that when I move the 7/10 over to the other side, it becomes a 10/7. Again, doing math kind of fast there. And then reversing the order and taking the square root, I get 10/7 GH. And I don't know why I made my square root so big, but I did. Okay. All right. Let's compare and contrast here, right? Which of these two boxes says that the velocity is higher or more? The one over here in black, right? Okay. 2, the G and the H, they're all the same, aren't they? Square root's the same. The only thing that's different is the thing in the front, 2 or 10/7. 2 is bigger than 10/7, right? Which means the rolling bowling ball gets to the bottom going slower. Why is it going slower? They both started with the same potential energy. It's actually kind of sort of the friction. That's not it. Some of the energy that the ball started with had to go into rotational energy. So if there was let's just invent some numbers. Let's say both of the balls start with 10 joules of potential energy, right? How much of that potential energy for the ball that doesn't roll gets to be turned into kinetic energy for the center of mass? All of it. 10, it has 10 down here, doesn't it? Okay, all right. Over here, if we start with 10 joules of energy, pseudo trick question, how much energy does it have when it gets down here? It's 10. The answer is always 10, right? But the problem is, let's say 3 of those joules are tied up in rotation. What does that leave the remainder as? 7. And that 7 will be in the kinetic, like the V, right? The linear translational energy that the ball will have. Let me put this maybe into a different context for you. This is the one time the biologists are going to get to rejoice. Okay. Field trip to Africa. Okay. We've gone to the Africa. We're on the savannah and we're watching all the animals trying to eat each other. Okay. So, an antelope. Okay. What does an antelope's leg look like? Ham? All right, Gavin's hungry. All right, so this will not be a drawing of an antelope. This will be a drawing of an antelope's leg, right? Okay, so an antelope's got like a big hippie thing, and then it's got a really slender leg. It has knees and things, but I'm just going simple here, right? Okay, so an antelope's got like a lot of its musculature in its leg way up high, okay, and very little way down low. There is a sort of axis of rotation in the hip, right? And the question is, why do antelopes have legs like this? What could possibly be the evolutionary pressure that would allow antelopes to be successful on the African plain? Why would they need to move their legs faster? What is an antelope's primary defense mechanism? Multiply and replenish the earth. Run away, right? Like, okay. They are food, right? They have some horns, but mainly they just use that to bang each other's heads, okay? But the idea here is you want to get moving as fast as possible, right? So why have all the muscles up high? Okay. It's not so much center of mass. I mean, okay. So why isn't their leg look like this? What do you mean it'd be harder to move? What's different? The mass of those two legs is the same, even though I did not draw it that way. What's different? Well, the axis of rotation, still up there. It's the distribution of where the mass is, isn't it? What are you guys running around in your idea, in your mind? You're circling but not landing. There's no antelope leg up here, Mr. Balogh. Where are you? But there kind of is, right? Because we can put like, I don't know, a solid cylinder and a slender rod together or something like that. But the point is, if your mass is concentrated near your axis, what is your moment of inertia going to be compared to having all your mass way out at the end? This is much bigger, much bigger. Remember, that moment of inertia goes as mr squared. It's like all over this chart, isn't it? We argue about what number goes in the front, but in the end, it's like mr squared, right? And it's this, where is the mass at different radius? Here, the mass is all at very smaller radii, right? Over here, right? All the antelope that had legs that looked like this got eaten. They did not pass on their genes, right? Okay, so evolutionary pressure develops, right, an animal that can run away from all the tigers. All right, why is it that cyclists don't fill their bicycle tires with like lead? I mean, the tire would be stronger, wouldn't it? Why don't they do that? Why is it that a fancy, expensive racing bicycle costs so much money? I don't even want to talk about it. Moments of inertia. Okay, so why do they want the tires to be as low moment of inertia as possible? Less energy into rotation, more energy for what? Vroom, vroom, right? And beat the person in the race, okay? So again, these are all considerations that need to be taken into account now that we understand or at least know about rolling motion. Moment of inertia affects these things. Energy is always conserved, but now we're splitting it up, right? For things that are rolling without slipping, you always have to share some of the energy has to go into rotational kinetic energy. And if it's in rotational kinetic energy, it can't be in translational kinetic energy, the 1/2 mv squared, right? So keep that in mind. To put it a different way, right? If I have my bicycle wheel here, right, and it's rolling along the surface of the table versus it not rolling and me moving it at exactly the same speed, which of those two cases has more total energy? It's the rolling one. Why is it the rolling one? They were going at the same speed, Mr. Balogh. Shouldn't they be equal? When I say they're going at the same speed, what am I talking about? The speed of the center of mass, right? Speed is v. If I wanted to be very careful and talk about its rotation, I'd say angular speed, and I'd be meaning omega. But if both of these have exactly the same center of mass speed, then they both have the same 1/2 mv squared. It's just that the one that's rolling also has 1/2 I omega. So in those two cases, the energies are completely different, right? If we rolled if we just sent one of them, say, into a ramp, right? And it's just like frictionless and it's just sliding and it goes up the ramp, versus we take one that's rolling, moving at exactly the same speed, and which one's going to go higher up the ramp? Which one has more energy? The rolling one, right? And so it's going to go up the slope higher, right? Just to put some numbers to it, if this one has 10, the rolling one has 15 or more, right? It just has more total energy, and so it's going to go higher up because of that more energy, right? So the confusion I can see in your eyes, some of you are like, did you just say the opposite? Not really. If we start at rest and we have one that slides versus one that rolls, what do we know about the energy of both of these objects? It's exactly the same. They start with the same energy, which is why one of them will be slower because some of that energy goes into rotation. That's different than me saying they both start with the same speed. Speed is the center of mass, right? But if one of them is rolling and its center of mass is going the same speed, it has the same 1/2 mv squared, but it has an additional 1/2 I omega squared, right? And because there's different energies, we will have different heights going up. So you gotta be careful. All right, let's do a quiz. Okay. The time has come for torque. And we've put it off. So what have we done so far? We've done kinematics, right? For things that are rotating. Omega equals omega naught plus alpha t, that, the toolbox, all that sort of stuff. And then we did energy, right? Conservation of energy, where we introduced concepts of moment of inertia and rotational energy, something that we have to keep track of now. So we've put off forces kind of as long as we can, right? And what's the problem with forces in Newton's second law? It's all the equations that like erupt, okay? It's going to be bad. I'm just letting you know right at the outset, right? I'm not going to sugarcoat it. It's Newton's second law. It's going to blow up and it's going to be horrible, right? But let's talk about what torque is first. I need a volunteer. You will not be harmed and you don't need much strength. Need somebody to come up here and help me. Anybody? Anybody? Redeem, thank you. Was it the not getting hurt or the not much strength that convinced you? Both. Okay, all right. Redeem. Would you please, everybody give Redeem a hand for being brave. And okay, very good. Redeem, would you please spin the wheel? Okay, notice, do it again, kind of in slow motion. Which way is Redeem pulling or pushing the wheel? It's kind of a downward motion, right? Okay. And what did the wheel do in response? It rotated, didn't it? Okay, Redeem, can you spin it the other way? Ooh, what did Redeem do? When his force, which direction was his force? It was upwards, wasn't it? To get the rotation to happen. You're good. Okay. Now what I want you to do is I want you to put your hand right there on the wheel, okay? And I don't want you to push up or down. I just want you to push directly toward the axle of the wheel, like as hard as you want to. Right? You're pushing, right? Okay, right? Okay. Notice what the wheel wasn't doing. It didn't rotate. We were applying a lot of force, right? Okay, spin the wheel again. Was that a lot of force required? Redeem? Not at all, right? Okay, I give Redeem a hand. My lovely assistant, thank you. You can sit down. All right. What was the difference there? Why did the wheel rotate with an up or down tangential force versus that strong axial or radial force? It was all about direction, wasn't it? Okay. Torque is rotational force. So far, we've had sort of these analogs, right? We had V and we had omega. We had A and we had alpha. There was a linear thing and then there was an angular thing. We did the same thing with mass, didn't we? We have moment of inertia now. That is I always call it rotational mass because that's kind of the role it plays in rotation. So when it comes to forces, and what's a force? It's a push or a pull, right? Okay. A torque is a push or a pull that causes rotation, right? If you have a push or a pull that is not causing any rotation, that's a force, right? But if you take a push or a pull and you end up with rotation, then what has been applied is called a torque. For those of you that are going into engineering fields, you will call these moments, because apparently you're going to have many moments while you're thinking about that. But yeah, that's what they call it in engineering, moment, okay? Which is why we call I the moment of inertia. In engineering, moment refers to rotation. But in here, we're going to call it what it is, which is a torque. So how do we like put all of this together and think about it? I'm going to, let's see here. How do I want to do this? Let's draw you know what? I did the example with the wheel as a circle. I want to do a slightly different shape to just drive home the idea here that torques and rotations don't always have to happen with circular things. And I want to use the example of this right over here. What's this? This is a door. Okay? Is it shaped like a circle? No. Does it rotate? Yes. Okay. My old room, I had a door up near the front of the room, and I could use it for more examples, but I can't because this room is dumb. And it's got an abomination in it. It doesn't have any doors in it. Boy, I tell you. So what we're going to do, I'm going to draw top view of a door. Okay? What does the top view of a door look like? It looks like that, right? And it's got its hinge over here, right? Okay, where it's attached. And it's got its doorknob over there, right? Where we go to open the door kind of thing, right? And let's just say for the sake of argument and generalness that somebody walks in, normal people wouldn't do this, but somebody walks in and applies a force like this. It's not terribly effective to open a door like that, right? You want to push directly on the door. You don't want to like push at a side, right? Okay. But in fact, that's what some person is doing. Okay. Is there going to be a torque? Will there be a rotation of this door? Yes. However, this force is broken into two different parts, isn't it? Okay. There is a component that's kind of along the door, and then there is a component that is perpendicular to the door. Which of those two components is going to cause the torque? The one that is perpendicular to it, right? Just like we saw that Redeem demonstrated for us, right? You have to have a perpendicular or tangential force, right, in order to cause the rotation to happen. If you have a force that's like pushing or pulling directly toward or directly away from the axis of rotation, nothing is going to happen. You're not going to get any torque. I should have labeled my axis right there, okay? So, torque is symbolized with the Greek letter tau. Now, this Greek letter, it's kind of weird. So a T, right? It's got a crossbar and the part of the T goes above, right? The crossbar kind of thing. In the tau, like technically it's supposed to be like a sort of I don't know, like a squiggly top or something like that, okay? Most physicists, we don't have time for that kind of nonsense. So sometimes we will do this, right, just to give it sort of a little squiggle. But then you've got physicists like me that just do that, right? The difference between T and tau, though, is that you don't go above the crossbar, right? That's how you tell the difference between a T and a tau, as well as from the context, right? Are we talking about torque? Well, those T's are probably taus. Okay, so the torque Okay. Now, okay, so we're actually going to write torque a lot of different ways in here. They're all the same way, but they look different. And we're not going to do the full vector torque until later. So I'm going to go ahead and take this off. Torque is a vector, just like force is a vector. But let's just get our minds wrapped around magnitudes first, and I'll show you some problem solving. And then when we get to chapter 11, we're going to get a little bit more formal and talk about the real vector nature of torque. So we'll just leave this as magnitudes for right now. Your book will probably tell you, I know it tells you, I looked it up, okay, that it's r times f times sine of the angle between the vectors. They sometimes use a different angle, like phi, instead of theta, because we already used cosine theta for a dot product. More on that later. So this is how your book would do it, and your book's not wrong. But I want you to know that the box in blue is a trap. It's a big trap. We need a radius. So the radius is the distance from the axis of rotation to where the force is being applied. If I take a force, right, and I apply it on the side of my wheel here, out at the edge, right, I give a certain amount of torque, right? Okay. But if I come in right here and I apply the same force, what happens to the amount of rotation? It's a lot less, isn't it? So if I apply the force out here, see how I get quite a bit of rotation there? Versus in here, giving the same push, right? I don't get as much rotation. So torque, the amount of torque, does depend on how far away from the axis of rotation I am. If I come over here to this door, right, where do I push on the door? The axis of the door is right here. I'm sorry, you can't guys see this very well, right? But the axis of the door is on this side. So where do I push? I come here to this side, right, to push here. Why? Less force is required to get the door to. If I try to do it, don't latch it, right? Take a lot of force. But if I try over here, that was not an exaggeration, and I am a weakling, right? But it's hard right here, right? Why is it hard close to the axis of rotation? I can't produce as much torque with that smaller radius. I have to apply more force to get the torque to rotate the door. Which is why me, Mr. Balogh, I like to write it as that distance from the axis perpendicular to the force that is being applied. That symbolism right there of that sort of upside down T between the R and the F, that means perpendicular to. Oh my goodness. Did I spell that right?
Yeah, you did.
I should think less often. I even wrote it kind of clearly. Jeez. Perpendicular to. All right. So the reason I like to write it like this is it's a direct, in-my-face reminder that if I'm going to find a torque, I need to make sure that R, the distance from the axis, and the force I'm using are aligned how? Perpendicular to each other. So in this example, right, if I had my angle right here, what component of that force would I use? F sine phi, right? Which you're like, well, Mr. Balogh, that's what's in the blue box. Okay, fine. That's what's in the blue box. But what if the angle were given right there? This is now F sine theta. This is F cosine theta, right? And now it would be R times F cosine theta. A little bit of inside baseball here for you. I don't understand why physics textbooks, and almost all of them do this, I don't understand why they insist on giving you RF sine of an angle, which is a trap, because what does every new person assume about what's in the blue box? It's correct, it's the gospel, it's like, it's always going to be what it is, right? But it betrays an idea. The idea that we need this perpendicular components in order for this to work, right? And the texts universally completely ignore the skill that we've been trying to build in you from chapter 5 onwards, which is finding components of forces, right? Why don't they say you need the component of force perpendicular to the moment arm? I don't understand. It's just, well, I kind of do. So the reason is that RF sine phi is a mathematical description of something called a cross product, which we are going to get into in chapter 11, okay? Cross products are a type of vector multiplication, and yes, the magnitude of the cross product is equal to RF sine phi, so it's just easier to just do that. No, it's not. It just isn't. R perpendicular to F is going to save you over and over again. It will orient your brain. It will free you from the tyranny of angles, because you'll just look at your angle and it's touching, not touching, and you'll know whether it's sine or cosine, and you will go on with your life and you will be happy. Okay. The reason I will never, ever write a textbook has two very important pillars to it, okay? Number one, I can't stand writing. I hate it. It hurts me to do it. My learning disability targets that ability. It's hard for me to spell and write and put sentences together on the page. I can speak it all day long, but I just can't write it. That's number one. Number two, so my life would be an utter hell and a misery if I just had to write. Second thing is, once you write a textbook, you are a slave to the publisher for the rest of your life. Because, I shouldn't use the word slave. That's a little bit too, that's hyperbole. I am an indentured servant to the publisher for the rest of my life, because they will demand updates and corrections and new editions to charge students more money. So no. I do that. I do not monetize my YouTube videos. Anyway, so yeah, sorry. There will be no Mr. Balogh. Although I have to tell you this story. Young man in my church congregation came home one day from college for Thanksgiving or Christmas or something like that, and he ran up to me. He's like, Brother Balogh, I saw your name in my physics textbook. Okay. He's like, you were one of the supporting authors. I was like, yeah, I corrected some things in their text. I edited a few chapters, and I told them where they got things wrong. But apparently I had been listed in the many authors of the book. There's like 100 of us in that book. But yeah, so my name is out there somewhere. You know, they haven't asked me to do that in a long time. Yeah. That was too harsh. Told them exactly where they did it wrong. I probably told them something like, don't use RF sine phi. And they're like, this guy's nuts. All right. So I like to use R perpendicular to F to just get my brain into the right mode of thinking that I need perpendicularness. Now, I'm going to point this out, and it's going to kind of break you a little bit, but it's going to come back in chapter 12. So let me break your brain just a little bit right now, so that next time you see it, your brain is just a little bit broken, and maybe we'll get back, be able to figure it out. Same setup. Axis is over here, okay? Notice how in this setup we went and looked for the perpendicular, like we went for the components of F, and we found the part of F that was perpendicular to this distance right here. So there's another way to think about this, and it's called the line of action of the force. This force is acting along this line right here. If you find the perpendicular distance to that line of action of the force, you will get exactly the same answer as you got up here. Again, it breaks your brain a little bit because like, well, what's the angle? Okay, well, I don't know. The angle could be over here. It could be over here. I don't care, right? But if I can find this distance right here, which is perpendicular to this line of action, I get exactly the same torque as if I found this distance and the perpendicular part of the force. Now, we will exclusively do this in chapters 10 and 11. Okay? We're going to come back to this line of action of the force idea. We're going to come back to that in chapter 12 when we're doing something called statics. And it's going to save our bacon there. It's really going to come in useful there. Okay? But I just wanted to kind of point it out just to emphasize again, right? These two things have to be perpendicular to each other. They don't have to be attached, okay? They just need to be perpendicular to each other. So either find a perpendicular component of the force or find the perpendicular distance to the line of action of the force. Both are going to work. Okay, so let's see if we, totally failed in teaching you another very important thing. Do you remember, I know you remember with trauma, Newton's second law, right? Okay. You want to take a guess as to what it looks like in rotation? Instead of M, what are we going to write? I, the rotational mass, right? The moment of inertia. Instead of A, alpha. And instead of sum of the forces, sum of the torques. Good luck. Have fun on your homework. Bye. No. You know what's going to happen, right? With Newton's second law, what always happens with Newton's second law? You get components, it like blows up, doesn't it? One little equation turns into like 4, right? And you're like, what the heck? How did that go bad so fast, right? It's going to do it again. Okay, so let's do this example, okay? So potter's wheel, you got a picture down here, right? The wheel, right? Wheels on the bus go round and round. Well, they go round and round on the potter's wheel too, right? And if you get it right, you get a bowl. If you don't, you get deformed bowl. That's basically all I've been able to make on a potter's wheel, okay? But this person's doing pretty good. So we've got a situation, right, where the potter is like turned off the power to the wheel and is trying to get the wheel to come to a stop, right? The wheel's been in rotation and now we're going to bring it to a stop, okay? So, and this is kind of interesting, just especially based on what I've just sort of described to you. Come on, thing. Pause. There we go. Okay. So this potter takes like a rag, right, and presses it radially inward. Now, how much torque is that 70 Newton force producing? 0 is the answer. Why is 0 the answer? It's not perpendicular, right? It's pointed, like, what would be the radius? Like, where would we draw the radius for this torque? It's the dotted line, right? Okay. Here's my radius. Here's my distance from the axis of rotation to the point where the force is being applied. But the force and the radius are not perpendicular to each other. So how is this thing going to slow down? Are we going to have fun? Okay, So we do need to sort of specify some things. Choose your own adventure. Is it moving clockwise or counterclockwise as seen from above? Counterclockwise? Okay. It makes no difference. So we know that this thing was rotating, right, counterclockwise around that way. So if it's going that direction, right here where the rag touches, what direction would the kinetic friction be pointed? What's the other way? Clockwise. So which direction do I draw my kinetic friction at this point right here? Up or down? Up. Okay. So here is my kinetic friction, and it's that kinetic friction that's causing the torque, isn't it? The 70 newtons is like a type of normal force, isn't it? Pushing into the surface of the potter's wheel. It's the kinetic friction that is perpendicular to the distance from the axis of rotation that is providing my torque. Okay, good. So we've kind of got that sort of set up. And what am I drawing over here? What is this called back from chapter 5? A free body diagram, right? Okay, it's got forces on it. In this case, when it comes to rotation, we do need some idea of the shape of the object. Before, when we did the shape of the object didn't matter. Now the shape of the object matters. So yeah, okay. So we're kind of getting there. But a free body diagram wasn't just a picture of the forces. It had another key thing that we had to define. What was it? Coordinate system, right? We had to be able to talk about the coordinate system, like what was positive, what was negative, all that sort of thing. So what we need to do is we need to pick a direction, a positive rotational direction that we can base all of our writing of equations on and everything, right? So back in chapters 5 and 6, I gave you a rule of thumb, right? A way to stay safe in setting up the problems. What was that? No, that was chapter 9, 10. Always follow the acceleration. Make your positive direction for your coordinate system following the acceleration. So we've got to answer the question, which way is this thing accelerating? Okay, well, we know it's rotating counterclockwise, right? So if this thing is rotating, is that counterclockwise for you? Good. Okay, if it's rotating counterclockwise, right, and I'm going to come in with my wet rag and I'm going to push on the edge, right? Okay, which way is the acceleration? It's clockwise. How do you know it's clockwise? It slowed down, right? So that means that our alpha is this way, right? And so I'm going to go ahead and specify my positive rotational direction to be clockwise. That entirely depends on the direction we chose for the original omega, right? If we had said omega was clockwise, then alpha would have been counterclockwise. Something that slows down has an acceleration and velocity that are opposing each other, right? If something's speeding up, what do? Same direction. And if it's not changing its speed, acceleration is 0. Okay. I draw an arrow, right? It's either an arrow that loops clockwise or counterclockwise. I put a plus sign in the middle, right? Okay, just to indicate this is my choice of positive direction. You can also, for clarity, write a CW or a CCW across the top of it or something, right? Figure out a way that works for your brain to remember which way you're called positive and be able to communicate that to other people, right? Clearly, to say, okay, this is the direction. It's not X, it's not Y, it's clockwise or counterclockwise, right? Those are our two rotation dimensions, if you will, directions. There's only one dimension to rotation. Okay, so we've established some forces. We know our positive direction, okay? There's only this one force, the 70 Newton force, and its associated friction that is causing this change in motion. So I don't need to think about any other objects. And now they want us to find the coefficient of kinetic friction, right? Okay. We start with Newton's second law in rotational terms. It's rotating. We've got alphas. We've got a torque. We might as well do it this way, right? Okay. Now, we need to start figuring out the pieces parts that we have here. I'll leave it up to you. Where do you want to start? Do you want to start on the left-hand side or right-hand side? Left. I heard left first. Sorry. Left wins. I've been trying to give you guys a lot of choice lately. You notice that I let you choose the colors of the blocks yesterday? Okay. I'm giving you the choice today whether we start on left. Why is that? To give you the illusion of choice. Okay. This is not a democracy. It's a benevolent dictatorship, right? And it doesn't matter. The choice of whether we go left or right doesn't matter. The choice of your colors yesterday, guess what? Didn't matter. Just was fun. For me, maybe. All right. So we'll start on the left-hand side. Moment of inertia. We need to figure out the moment of inertia of this thing. How are we going to figure out the moment of inertia of a potter's wheel? Aha, the table. The answer is in the table, right? If it's not in the table, it's the square root of 2gh. If it's neither of those things and you're in philosophy class, the answer is 42. Okay, so we need a table. Oh, well, we need to know, okay, what is a potter's wheel? What do they tell us? Thick stone disc. All right, so that means that somewhere on this table, okay, it's never the yellow ones. F? The solid cylinder? Yeah, the potter's wheel doesn't have a hole in the middle, right? Okay. By the way, we're going to use this one in lab next Wednesday. Okay. And this one and this one. Anyway. Okay. But like, yeah, I'm thinking solid cylinder here, right? Okay. And they gave us the mass and the radius of the potter's wheel. So if they don't give me any other information, I'm going to go with what I think, right? It's got so 1/2 mr squared is what that says. So my moment of inertia, I'm going to assume, is 1/2 mr squared. And I was given the radius, 1/2 meter, and I was given the mass, 100 kilograms. That's a big potter's wheel. That's like 220 pounds. Okay, so I got that. All right, alpha. Do they give me alpha? No. Do they give me enough to tie my own rope to find alpha? Unfortunately, yes. Because what have they given me? They've given me an initial omega, and they've given me time. Dead giveaway that we need to use what? Am I now allowed to mix kinematics and torque into a single problem? Yes. Why? It's in the chapter. Right? Up to this point, kinematics was a different unit than Newton's laws. Right? Okay. It's all happening in the same chapter. This is your worst nightmares come true. All right. That's okay. It's okay. It's okay. We can do this. Omega. My final omega is what? 0, right? It comes to a stop, right? My initial omega, 50 revolutions per minute. That's not a standard unit. We'll fix that in a second. Alpha, I don't know. T is 6 seconds. What equation is that? How do I find alpha if that's all I know? That's the first equation, isn't it? Right? So we got to convert alpha. We'll get okay, fine. We'll just do that right now. 50 revolutions per minute. I'll show you what I did. For every 1 revolution, there are 2 pi radians, and for every 1 minute, there's 60 seconds, right? So I'm going to take 50, multiply by 2 pi, divide by 60, and I got 5.24 radians per second. So I now have my alpha, no, my omega, and my alpha is going to be final minus initial over the time, doing some algebra there that I completely skipped over. I got negative 0.873 radians per second squared. Okay, why did I get a negative sign? It's slowing down, right? Okay. We aren't very careful with like what we're calling positive and negative when it comes to kinematics, right? It's sort of implied as to what's going on here. But that negative sign just means that our alpha is opposite our omegas, right? I am not going to include the minus sign when I eventually plug this alpha into here. Why am I not going to include the minus sign? I've specified a coordinate system over here, and I've already taken care of the directions in here, right? All I need really is the magnitude of alpha. So don't be literal. Like when you're using kinematics, don't like, oh, negative, I'll put negative in here. Now you've double corrected, right? And you're going to end up with something that doesn't make any sense. So just be a little bit careful with your signs, right? Once you specify a direction over here, you're just putting in numbers at that point. We'll put negative and positive signs on the things themselves. What do I mean by that? Well, now we have the left-hand side that we got to worry about, right? Vector signs come off because I'm going to be putting in some forces here, and I will make sure I get the directions of the torques correct, right? So, how many torques are there in this situation? One. Technically, there could be two, but one of them has a 0 next to it, right? Okay. So the 70 Newton force is not causing a torque, but the kinetic friction is, right? So watch what I do. I'm going to write tau, torque, of kinetic friction. Torque sub kinetic friction. Okay. I just write the symbol tau and a little label on it that says I know that there's a torque from this friction. I'll figure it out later. At this point, when you've identified the number of torques, and there's only one in this problem, you go back and you say, okay, is that torque positive or negative? And how do you tell whether the torque is positive or negative? Remember, it's an R perpendicular to an F. So let me show you a trick. You take your pencil. You hold your pencil such that one end of it is at the center of your axis of rotation. You hold it down with your hand, okay? And then with your other hand, you apply the force in the direction of your diagram. My pencil rotates which way? Clockwise, okay? And clockwise we defined as what? Positive. So I'm holding it here at the axis of rotation, and then I come along and my force is up, and as I push up with my finger, which way does my pencil rotate? It rotates clockwise. So this torque is a positive torque. The pencil trick works. Try not to show people in the library, they'll think you're nuts. So I'm going to put positive right there. It's going to get a lot worse. You're going to be doing pencils, you're going to be doing right-hand rules, people are going to wonder. All you have to do is say, I'm in physics class, and they'll go, okay, and they'll leave you alone. Okay, so I know my I. Like I can go calculate this. I found it to be 12.5 kilogram times meter squared. Okay. I know my alpha. We calculated the alpha, right? Now I need to write down what my torque is. And what's torque? It's R perpendicular to F, right? It's R. And what's my perpendicular force? The kinetic friction, right? Those two things are perpendicular to each other. I don't have to go find a component of kinetic friction because it's already at 90 degrees to my radius, okay? But, okay, so I know I know alpha, I know R, I don't know F. And I still don't have like a coefficient of friction in here somewhere. Where's it hiding? Thank you for doing the pun for me. R times mu times... Run! Everybody run! Run! Oh. And do we know the normal force? What's the normal force? 70, right? So I can solve this for my coefficient of friction, and now I can chuck all of my numbers in. 12.5 times 0.873 all over my radius. 0.5 and my normal force 70 gets me a coefficient of 0.312. What are the units on coefficient of friction? No units. It's the only number you can leave and have any units on it, and I won't be mad.
How come your normal force was the
70 is what's being pushed into the side of the wheel, coming in with a 70 Newton force, and it's normal. It's perpendicular to the surface, and it's related to the friction. It's coming in this way, normal to the surface. It's safe to say that your brains get filled about 25 minutes into lecture, and we've been going for 75 minutes. So we'll leave it at that. Have a fantastic weekend, because I won't see you tomorrow, even if you're in grasp. But you have enough now to get most of your chapter 10 homework done. So try to get as much done as you can. We are going to tackle this problem on Tuesday. You've seen it before, but now the pulley is going to be real.